This has the same um, um, disclaimers as the other one. Most of this is pulled like straight out of Theory of Computation, and we just did chapter 8. So yeah, I reused some stuff and whatever. I don't feel like fixing it all. We have our definitions, and I think like visually, the parts of this that I think about are when we have um, so we have big O is our upper bound, and then big omega is the lower bound, and then big theta is the tight bound. So when I look at these, especially when we have like polynomial time stuff, so if we have a curve that's like this for our big O, and then we have a big omega, and then we have something in the middle. That's our big theta. So when we're, oh yeah, it goes across. And then this is the parts in there where it's like we have this, we have a narrower range of where an algorithm is most likely to end up. So that's the typical case. And then big O is worst case, and then big omega is best case. So when we're looking at like search algorithms and stuff like that, big omega can actually just be like 1 if it's the first thing in line. So we tend not to actually calculate these things off of like specific sets, which is what the rest of the little proofs are. Cross. Oh, that should say f of n. So these are all qualities of functions, not qualities of a specific data set, which is why these don't necessarily follow if we have a specific data set where the first item in an array is the one that we're searching for, then that will always be constant time. But this is an analysis of the algorithm itself or the function itself, which in this case, the same thing. So this is also kind of a good example of when we talk about different sorting algorithms, how on average they will be significantly less than their worst case or their sorry, I'm having allergies, so my eyes are leaking. Um, Degenerate cases where with big O, that's when we have to look at like every single item, and the last one is always the one that we're looking for. So when we look at some of these functions, some of them have been analyzed down to like some matrix math. I think is like it's like 2 point like n to like the 2.36 or something like that, where we have taken like all of these collections and actually analyzed them down and said like, okay, this is the average case over the trillions of runs that we've done based off of real world data sets and stuff like that. So those are usually going to be the big thetas. But specific to these, like by now we kind of have a good gut check. Like if we've gotten to this point in math, we can say yes, this is always going to be the dominant part. So then we can look at this and just be like, yeah, that's big O of n squared, polynomial time. Seeing as this is literally just a polynomial. So a polynomial runs in polynomial time, which is kind of obvious. But I think the proofs kind of like force you to really think about what we're doing with most of these algorithms. And this is kind of the giveaway, is that this isn't normal math in the sense where we could end up, plotting this and having that math intuition be like, oh, this is some sort of parabolic where, we could have negatives, or, we can have numbers that don't really exist. In this case, if we're talking about running an algorithm, we're running it on something. We're not running it on a negative data set. So it's going to be counting like iterations through the algorithm. So my takeaway with this is like when we prove these, we push all of these to where we have, there exists some constant greater than 0, and there exists an n naught that is, a natural number. That in all cases n is greater than or equal to n naught. Then that's how we get our big O. So what we're doing with this is pushing these equations to where we're shifting everything into being these greater than 1 type scenarios. So we're pulling out all of the cases where we would be like negatively computing something, like we're decomputing something, which doesn't make any sense. So in this case, we can literally use n naught of the n squared and apply that to all terms. And then this satisfies the sum constant, being the 18 times the n naught of our n squared, which satisfies the n greater than n naught equals 1. So the definition is satisfied, which, I don't know, it seems like a lot of sort of esoteric math just to say, hey, if you're running this on a real number of times, this is what the upper bound is going to look like. I don't know. Maybe I'm missing something, but that's what it feels like to me. Same thing here. There can be no such constant and n naught that satisfies big O just equaling n starting from n squared, which is like basically just saying if the only way to get a big O of n for a polynomial growth type equation would be breaking these definitions with our constant and n naught. So this asserts that every integer n greater than n naught is bounded above by a fixed constant c. To produce the contradiction, simply choose any integer of n whatever, so that the assumption breaks, which is basically just breaking an inequality. So again, if we're running this forwards in time space, we're never going to end up with an upper bound that is less than polynomial time for that. This one is way more complicated, but we're looking, we're kind of just assuming some infinite sets here, and then proving that they all end up reducing to n log n. So n log n over 2 minus n log 2 over 2 is still n log n. which this one was kind of surprising. So at least this one wasn't just like stupidly obvious, which maybe that was why you ran them in this order. Being like, prove that a polynomial runs in polynomial time. Yeah. So insertion, sort, complexity analysis. The higher level of this is that we have a loop in a loop. So we have an inner loop and an outer loop. And what do these end up meaning is that we're always going to end up in like we're always going to end up in polynomial time for worst case, and then the best case is that it's constant time. And that was the drawing that I started saying is we can analyze something where the first loop is going to have some sort of n, whether it's like n plus m or n plus whatever, whatever that dominating term inside of that loop, and then doing that another n number of times is always going to be n squared. So the worst case is always going to be that n squared polynomial time when you have loop loop loop, or if like I said, loop loop loop, then we're going to be running through 3 iterations of n, but that's all still just polynomial time. And in this case, when we run through this, we get the best case complexity is just constant time, where we pick a spot to go into this sort and we're like, oh, everything's already sorted. But that still means that we have to go through each element. So it's not just like big O of 1, like some search algorithms can be. So if you just happen to pick the right element, yeah. So this is just proving that the best case complexity, you still have to go through every single element in the set and just show that it's still already sorted. And then the average case is what I was just talking about. We may only have to go through, like, if our outer loop and our inner loop, even if we only have to go through n minus m in each of the loops, like some things are sorted and some things are not, then while we're going through that, we still end up with some constant times some constant, which is going to reduce to polynomial time. So the average time and max time end up being polynomial time. But in practice, there's some that the real calculation usually is going to end up being some sort of like scatter plot averaged over whatever. And this is what I was talking about. The inner loop and the outer loop have complexity n, so the full set is going to be n squared. So this is kind of just a duh statement, but it was requested. It's optimal for nearly sorted inputs. If you're sorting data that's already sorted, it's going to go super fast. Which is why standard library implementation of quicksort and merge sort switch to insertion sort for small subarrays. So what that's saying is, relative to a large set, a smaller set is always going to be more relatively sorted. So we can optimize a sort overall by taking a smaller set that's going to run faster in insertion sort and using that in larger quicksort merge sort implementations. So on uniformly random worst case inputs, however, it's quadratic. It is dominated by n log n algorithms like merge sort, heap sort, quicksort. So this discussion is talking about how on larger uniformly random worst case inputs, then we're talking about the n squared average case and the n squared big O case. So when we have those larger sets that are completely random, or that we expect to be completely random, we're going to be starting off with, or at least having our implementation heavily dominated by n log n type algorithms like merge sort, heap sort, quicksort. So the discussion there is just how and when to decide that tipping point between using insertion sort, which can be faster than some of the n log n type sorts, and when to use just the n log n sorts or the combination thereof. So when a lot of these sorting algorithms are implemented, they'll run heuristics on their average data sets and then say, okay, this is the size of the chunk of our data that we should be using insertion sort on, and then putting that back into the larger part of the algorithm that's going to be running merge sort, heap sort, quick sort. So it's kind of like when you have data that is homogeneous by a certain demographic, then you can use insertion sort to sort just that demographic, whether it's people or some other like statistics and stuff like that. And then, yeah, I was looking into some of these other, the sorting algorithm visualizer. I think there's some notes in there about being able to use built-in heuristics and results on the way that any large data searching and sorting algorithm is going to give you the answer as to where that cutoff point is for which parts are going to be using insertion sort inside of their n log n sort. Holy shit, that was 20 minutes.